Hello everyone. In this video we are going to look at some engineering applications on roots of equations. So we have known some methods to find the roots of the equations. Those are the bisection method, the secant method, the regular falsy method or false position method, and the fixed point iteration method, and lastly we discussed the Newton-Raphson method. So these are the five methods we discussed in the previous videos to find the roots of an equation. And here we look at some engineering applications where we use those methods. So let us see this problem. A trough of length L has a cross section in the shape of a semicircle with radius R. When filled with water to within a distance h of the top, the volume V of the water is given by this equation. So a trough is there. This is a container. Trough is nothing but a container with length is L, and the cross section is like a semicircle. Cross section of this trough is a semicircle, and the radius is given R. So R value is given here 1 feet, 1 foot here, and the length of this trough is 10 feet, and volume when filled with water, the volume is 12.4 feet cube. Then using this information you have to find the h from the top. How much is the distance? H is from the distance from the top, and how much is this h within 0.01 feet you have to find. So we have to find the h value from this equation given the values of volume. Volume is this much, 12.4. L is 10 feet, and R radius is 1 again. So substituting these values here, only we have to find the h approximate to within 0.01. So let us try to form the equation first. Fx are here, f of h. This is an equation in h. So let me write again the V. V is given by this equation as we know. In this we substitute V. The volume is 12.4 and radius R is 1. I substituted that one. And then this will be 12.4 is equal to length. Length L is 10 times 0.5 pi 1 square minus 1 square arc sine. Arc sine is nothing but sine inverse. Sine inverse h by 1 because R is 1 minus h times r square, that is 1 square minus h square power 1 by 2. So here if we divide by 10, 12.4 by 10 equal to 0.5 pi because 1 square is 1, and arc sine h, that is sine inverse h minus h times 1 minus h square power 1 by 2. Further if we simplify, this 12.4 over 10 is 1.24 is equal to 0.45 pi sine inverse h. Arc sine is nothing but sine inverse h minus h times 1 minus h square power 1 by 2. And if we take this minus arc sine h to the left hand side, you will get plus arc sine h is equal to 0.5 pi, and take 1.24 to the right hand side, it will be minus 1.24 minus h times 1 minus h square power 1 by 2. So this is sine inverse h. So sine inverse h is 0.5 pi minus 1.24 minus h times 1 minus h square 1 power 1 by 2. From that you will get h is equal to this sine inverse. If we take the other side, so h will be equal to sine of 0.5 pi minus 1.24 minus h times 1 minus h square power 1 by 2. Now if we take this right hand side to the left hand side, h minus, you will get h minus sine of all this will be equal to 0. So this is an equation in h. So we can write it as f of h. So this is an equation in h. You have to find the root, that is h, for which h value this will become 0. So the root finding problem now is to find the root of this equation in the variable h. And if you observe, f of 0 is negative, f of 1 is positive. In fact, this equation is valid only for values of h between 0 and 1, because 1 minus h square to the power of 1 by 2 is valid. It is in the root. 2 power 1 by 2 is root. So root 1 minus h square is valid only when 1 minus h square is greater than 0. So this 1 minus h square is greater than or equal to 0 only when h square is less than or equal to 1. Therefore, h cannot be more than 1. H square less than 1 means h cannot be more than 1. So the minimum height from the top is 0. Okay, that means it is completely full. The height from the top is 0 means the trough or the container is completely full. In that case, h will be 0. So h always lies between 0 and 1. The maximum height we can have is 1, because the total height of the trough we have is 1 foot. Therefore, h is always lying between 0 and 1. Here, if we observe f of 0 is negative, you will get f of 1 is positive. So root lies between 0 and 1. That 0 we call the first a1, and this one is b1. Let us try to do this root finding using the bisection method, the first method. So using the bisection method, we take this equation f of h and we start with the two initial interval a1, b1. a1 is 0, b1 is 1. Then we find the midpoint. In the bisection method, we find the midpoint of 0 and 1, which is 0.5. And f of a1 at 0 we have seen it is negative. At 1 it is positive. Now we have to find the function value, this function value at the point 0.5. Here it happens to be positive again. You can check this one. At 0.5, we put 0.5 in this equation, we will get it is positive. So since the sign changes from a1 to p1, the function value changes from negative to positive between a1 and p1, the new interval will be a1 value here you have to write, that is a2 will be same as the previous a1, but b2, the second upper limit of the second interval will be same as p1. The previous midpoint will be the new upper limit now. This 0.5 we write here. We know this method how to do the bisection method approximations. Again, we find the midpoint of these two, which is 0.25, and the function value at this point, function at this x value. If we put 0.25 in this function, you will get positive again. Again, the root lies between a2 and p1. a2 and p1. So the new interval will be a2 value we write as a3, but b2 will be the p value, the previous midpoint 0.25. Again, we continue finding the midpoints until we get the error of order 10 power minus 3, because we want up to within 0.01. 0.01 is nothing but 10 power minus 2. 0.01 is nothing but 10 power minus 2, and we want within 10 power minus 2. That means we should get the error of order 10 power minus 3. So until we get error is of order 10 power minus 3, if we continue using this bisection method, then the approximation of the h value is 0.1640625. Let us go to another application of this root finding. The particle in the figure starts at rest on a smooth inclined plane whose angle theta is changing at a constant rate. So this is the rate of change of the theta with respect to t, and we call it as omega. Omega is negative, so the theta is the angle. So rate of change of angle is d theta by dt, which is omega here. And at the end of t seconds, the position of the object. So the position of the object is xt. X is the position, depends on the time t. So the position of the object xt is given by this formula here. G over 2 omega square times e power omega t minus e power minus omega t over 2 minus sin omega t. Suppose the particle has moved 1.7 feet. That means x, if the x is 1.7 feet, in 1 second, and that means the time t is 1 second. Find to within 10 power minus 5, and this is the error we need. Within 10 power minus 5, the rate w at which theta changes the changes. So we have to find the value of omega. So this is omega you have to find, given that x value is 1.7 and the time t is equal to 1, and this g, gravitational constant, is also here given as assume that g is not the gravitational constant here. G is given, g is equal to minus 32.17 feet per second square. So if we substitute these values in the equation, we see what we'll get in the next slide. So this is xt, the given equation. In that x, the position is given 1.7, and t value is given as 1, and g is given as minus 32.17. So after simplification, we'll get an equation, okay, 1.7 plus, if you take this term to the left hand side, plus 32.17 over 2 omega square times e power omega minus e power minus omega over 2 minus sine omega equal to 0. So this is an equation in omega. You have to find the value of omega where this becomes 0. Here if you observe, f of minus 0.5 is omega. If you observe in the question, it is given omega is always negative. So here you can see omega is negative. So at random we start with two initial values, minus 0.5. So the function value at minus 0.5 is negative, and this function value at minus 0.1 is positive. Therefore, the function changes sign between minus 0.5 and minus 0.1, and the root lies between these two, minus 0.5 and minus 0.1. So we start with the two initial values. P0 is minus 0.5 and P1 is minus 0.1. Let us use the secant method to find the root of this equation. Let us go to the next slide. So P0 is minus 0.5 and P1 is minus 0.1, and this is the equation. And in the secant method, this is the formula to get the approximations. Pn plus 1 is Pn minus Fpn times Pn minus 1 over Fpn minus Fpn minus 1. And this is the error given. So substituting P0 here, P0 which is minus 0.5 and P1 is minus 0.1 in this formula, and using the function f, we will be obtaining the first approximation, that is P2. When n is 1, P2. P2 is minus 0.3170454. Again, once you get P2, using P1 and P2, you will get P3. And after getting P3, using P2 and P3, you will get P4. Finally here, if you observe the error, we got 1 times 10 power minus 6, which is of order which is less than 10 power minus 5. So we can stop here where the root is omega is minus 0.317062 within 10 power minus 5. This is the rate of change of the angle, which is d theta by dt, nothing but omega. So this is how we see the root finding in different engineering examples using the methods we discussed before. This is the end of the presentation.